Welcome everyone. Avishua and I are here from the Wikimedia Foundation to talk a bit about how the fundraising analytics team, with help from our fundraising tech team as well as Brooklyn Data, modernized our data stack using DBT, Iceberg, as well as some other open source tooling. We'll do some quick intros, then we'll get into our agenda, where we'll talk about the context and motivation for these changes, an overview of the solutions, a deep dive into some of the tooling we ended up with, as well as outcomes, impacts, learnings, and takeaways. My name is Joseph Mando. I've been at the Wikimedia Foundation for a little over 4 years. Before that, I worked in data from junior to lead, business intelligence analyst, data analyst at various organizations for a little over 3 years, so close to but not quite 8 years working in data.
Hey folks, my name is Avishua Stein. I've been at the Foundation for 8 or 9 months now, doing data engineer and data platform work. And I've been doing this whole analytics thing in various roles in companies for 8 or so years now.
So outside of just the two of us, who is Wikimedia and why do we need to modernize our data stack for fundraising? Well, the Wikimedia Foundation is the nonprofit that hosts Wikipedia and other free knowledge projects, Wikipedia probably being the one most of y'all are familiar with. Our core mission is to make it easier for everyone to share what they know. And to do this, we keep Wikipedia and the Wikimedia sites fast, reliable, and available to all. We protect the values and policies that allow for free knowledge to thrive. We build new features and tools to make it easy to read, edit, and share from the Wikimedia sites. But above all, we support the communities of volunteers around the world who edit, improve, and add knowledge across the Wikimedia projects. The Foundation's main source of funding comes from small donations, which our fundraisers and advancement help drive from a variety of channels, like our banner and email programs. So there is more than one analytics team at the Foundation, but we work on the advancement and fundraising side of things. So that's what we'll be focusing on here today. How does analytics help with fundraising? Well, we create data models and dashboards that allow the broader teams in fundraising to effectively elicit donations through the various channels, like banner and email. And this includes servicing insights like conversion rates from our A/B testing programs, how different audiences are responding to different messages, as well as general file health metrics, such as are we hitting our fundraising goal in country X, channel Y? Are we growing our donor base? And this work supports the fundraisers, so they're able to raise the funds that support the work of the Foundation. So fundraising analytics, we're often reporting on revenue and donations attributed to those various sources, like I keep coming back to banners and email. And so in order to accomplish this, to streamline this, we built one big table that was called All Donations. So it was a model in our database. And this included donations back 6 fiscal years with attribution by source, location, and more. All the data for this model was being pulled and joined directly from our CRM database, which was on MySQL MariaDB. That CRM is Civi CRM, which we still do use today. And this resulted in a table with about 80 million rows, 100 plus columns from 12 joins. So big table. This allowed for reporting and analysis to be done from the same source though. So rather than just always having our analysts have to run ad hoc queries with complex joins, they could just reference this donation table. We also built the BI tool and other models downstream of this, so results would tie out across an ad hoc request or an already circulated dashboard as much as possible. But in order to fully rebuild this table on that stack, we would run this query via custom Python script on a schedule via cron jobs. Rebuilding this table took 5+ hours, which made it pretty impossible to do daily. So to solve for this, we had 3 total scripts to manage it. One that ran every 15 minutes to insert new records into the model. One that ran nightly in order to drop and rebuild the last 90 days of data, to remove refunds, keep the last 90 days of data fresh. Then the full rebuild, which only happened once a week on the weekend when hopefully people weren't hitting the database in the BI tool. The queries in these scripts were identical. We just had different date conditions in the where clause to manage how much table we were incrementally loading. However, if something needed to be changed in the model, we had to make sure we changed it in all 3 scripts. And long runtime also made testing new columns manual and time consuming. So, since we would only run the full rebuild once a week on the weekend, if a new column was requested, that meant the lead time could be up to a week in order for data to be fully populated throughout the model, to backfill it, since every day we were only rebuilding the last 90 days. Additionally, we were only able to accommodate that 6 years of clean attributed donation data due to the build and runtime constraints, and this made it hard to have the full context and trends in our BI tools, made it hard to reasonably expect users to self-service and drive their own insights. And it was also slow to query, which would mean hanging BI tools and thus hard to self-service. All of our downstream models would have these similar constraints, those being multiple scripts to build at different intervals to manage the runtime, as well as long lead times to populate new columns. Now, while we could do some of the more cosmetic changes, maybe a case statement as custom columns in a BI tool, it's not ideal because then those aren't source controlled. They're not code reviewed. Anyone can go and edit them. On top of this, we didn't have a great way to test and see how an update to one model could affect another model. The only way we were able to really do this, manually run them all, investigate any errors and failures ad hoc, which added a lot of time to development. It also relied on someone to really know what's going on across all the models. Even once we had these models pre-built in index, queries would still take a long time, often over 3 minutes if we're talking about the transactional data, which for end users trying to view in a BI tool is just, it's a lot to ask. We could aggregate downstream models and those would run faster, but this created a lot of overhead. So then we have more scripts, more tech debt. Over time, the program also has gotten more complex. Our fundraisers want to understand our donors in new ways to enhance our messaging and our strategies. But this also is going to mean new columns, new models, longer load times. So we had simply outgrown this current stack. So kind of getting into how this affected an end user, how this would affect a fundraiser. Let's say I am that fundraiser, and I'd want to know how revenue from the banner program has grown year over year. Well, I know there's a dashboard I can navigate to that has year over year views, filters I can apply. I navigate to that dashboard, I'm waiting for it to load. I'm probably waiting 3 minutes if it's built on that transactional data. I get there, I see all the data, I add my filters, I wait for more loading just to see that banner data. I see my data, but I realize it's limited. Maybe I needed to see back to 2017. The BI tool only has 6 fiscal years in it. I can't see back to 2017. And I also can't drill down for my own insights because of this long load times we have. And if I need to filter further, I know that's going to result in more waiting. So that just leads me to request ad hoc data from analytics, maybe even just the transactional data so I can pivot it out myself. So even our fundraisers, our end users had outgrown this stack and our workflow.
So, given these performance challenges, we knew we needed to upgrade our tech stack so our stakeholders could access more data faster. In addition to the challenges Joseph talked about, we also wanted to start integrating more data sources to support more use cases on the team. Whatever solution we went with would also need to provide a relatively frictionless way of adding additional extraction pipelines. We also had non-functional requirements, which I will now touch on. So we designed the new platform to be entirely open source and on-prem, primarily to ensure data security. Hosting on-prem allows us to deploy privately, reducing our cybersecurity attack surface. Open source gives us full control of the software, so we don't need to rely on SaaS vendors for data protection. For Wikimedia specifically, this approach fits well. My team, fundraising technology, already runs on-prem systems, so it's easier to build on the processes and tools we know. The foundation also has a strong culture of maintaining and developing infrastructure internally, as well as using open source, so our new data platform continues that tradition. Other advantages of keeping the stack open source and on-prem include lower hardware costs compared to cloud, and no vendor lock-in or forced upgrades. So, this is the stack we ended up with. We're using open source Dagster for orchestration, Trino as our query engine, Metabase for our BI tool, MinIO for object storage, Iceberg as our table format, Hive Metastore as our Iceberg catalog, and dbt for transformation. Soon, I'll dive a bit deeper into Iceberg, Trino, and dbt. So, as you may have inferred from the previous diagram, we chose a data lakehouse architecture for our new platform. Before I explain what a data lakehouse is, I want to quickly point out a key differentiator in 2 analytics architectures that came beforehand. A data warehouse is an architecture that, among other things, combines compute and storage. Compute refers to the capability of a system to process data and act on it, so things like joining data sets or calculating aggregates or doing filters. Storage is the capability of a system to actually store that data, usually in a special proprietary format that's conducive to analytics and only works with that data warehouse. Data warehouses and databases combine these features, so they're responsible for both the storage and compute. Data lakes, on the other hand, separate compute and storage. So your data might be stored in an S3 bucket, but you'll need to bring a storage engine like Spark or Trino or Pandas to actually manipulate the data before writing it elsewhere and storing it. So, what is the data lakehouse? Lakehouses address the shortcomings of both data warehouses and data lakes. Like data lakes, lakehouses keep compute and storage separate for flexibility, but use modern table formats like Iceberg to ensure interoperability. Some of the other benefits of a lakehouse architecture include Lower cost and flexible compute choices because we can bring our own query engine. Performance that approaches the data warehouse performance. ACID transactions for data consistency and quality. And data lakehouses also can more easily handle structured, semi-structured, and unstructured data. They also support schema and partition evolution. So here's a quick comparison highlighting some of the differences between these architectures. I won't go too deep into a comparison of the options, but ultimately we chose a lakehouse approach because it was scalable, performant, and open. So having given a broad overview of our architecture and tooling, I want to dive into some of the specific tools that are at the heart of the new data platform. Recall, like I said, compute or query engines, as I'll use them interchangeably, are responsible for taking commands like SQL queries or Spark queries and executing them on the data. We use Trino as our query engine. We chose Trino because, one, it's performant. We can toss some pretty large data sets at it, and it handles them really well. Two, Trino has a large community. There is a large Slack group where the maintainers hang out and you can get help. The GitHub repo is also very active, so you can open up issues. Third, Trino is federated, which means that we can query data that lives outside of just our object storage. We can, of course, query object storage, but we can also query our application database directly, Kafka data directly. So this means that we don't have to store as many copies of the data. We can just query it where it lives. Finally, there are many integrations with the other parts of our stack, like dbt, Iceberg, and Metabase. So many of the benefits of the lakehouse architecture that I just described really come from modern table formats like Iceberg. Iceberg defines how metadata is stored and managed across query engines and storage. The metadata used by Iceberg in these table formats make analytics faster and more reliable by helping query engines optimize queries, find the data they need, and not scan entire data sets. Iceberg also enables ACID transactions, which ensure data consistency and quality. Iceberg is also the system responsible for schema evolution, hidden partitioning, and time travel, making it easier for us to manage these growing, large, complex data sets. So, in summary, lakehouses depend on these table formats to connect the query engines with the object storage. We chose Iceberg because it integrates with our stack and is built on a really strong commitment to openness. Lastly, if you're here, then you probably already know about dbt and why it's great. But I'll quickly review. We use dbt to model our data, enjoy many of its benefits, including version control for our code, and also the CLI integration means that we can put it into our CI/CD processes and track changes to model definitions. Two, the ability to simply run parallel queries without a lot of config, so our jobs complete faster. There's a great community here. Of course, folks here might have gotten help on dbt Slack or in person at Coalesce and had great conversations. And finally, the integration. dbt integrates really well with our other tools. In the next section, Joseph will talk about some of the impact we've seen since moving to dbt.
Thank you. Yeah. So due to this new stack, we have seen huge improvements in performance just to the query speed, just due to the increases in query speed. So outside of dbt, focusing on the other aspects of the stack. How big of improvements? Well, rather than 5+ hours to build that model, that donations model we talked about earlier, now all of our sources and our marks build in less than an hour and a half. This means faster development as well as much faster deployment to production. And rather than a new column being backfilled over the weekend, we can do it same day once the development work is completed. We've also gone from taking over 8 minutes to query just 6 years of aggregated revenue data to getting 18 years in just over 8 seconds. I'm going to say that again because that's kind of the crux of where all of the gains have come from. It used to take us 8 minutes to query 6 years of aggregated revenue data. Now we get 18 years in just over 8 seconds. And this has improved the end user experience, not just the analyst experience, because instead of timeouts, users are now seeing more enriched data than ever in our BI tool. It also allows our analysts to be more productive and deep dive into complex analysis rather than waiting for queries to run or models to run. So let's go back to that example from earlier. Let's say I'm that fundraiser. I want to know how banner revenue has been growing year over year. I navigate to this, a similar dashboard. We made updates to the dashboard since we have some better query speed, but a similar dashboard, I navigate to that. And all the data has loaded much quicker because we've really increased the query speed. I'm seeing it load quick. I add my filters, and probably less than a minute later, I see more data than I need, but my initial question is answered. But also, maybe I see a spike in a particular year I'd not seen before, because previously in the BI tool, I only had access to 6 fiscal years of data. Now I have 18. So I drill down to the raw data. Maybe I'm doing my own filtering to see what was responsible for the growth. I'm trying to drive my own insights. I'm trying to see, can we pull anything out of there and put it into our current strategies. So rather than just requesting basic data from analytics, maybe my exploration has led me to something more complex I need an analyst to actually dive into. Or even just some questions on how I might be able to deep dive deeper myself, since that query time, the BI tool hang time is not such a variable. And our end users have raved about the speed. One in particular expressed to my team, they've answered so many questions for themselves they've been wondering for years in just 5 minutes. Removing query runtime, which has removed BI tool load time as a barrier, has allowed self-service, and we look forward to more users take advantage of this as we migrate more and more to the new stack. On the model development side of things, the analytics engineer side of things, as a result of all that new infra and work from myself, ongoing work from my team, and help from Brooklyn Data, we have the donations model. SQL is largely the same, some cleanup and tweaks for Trino and DBT syntax, but there are many quality of life improvements we've seen just with the switch to DBT, or implementing DBT rather. Most notably, rather than custom Python scripts, we now use just SQL files, which all run via DBT commands. We're also able to build and use macros and seeds, which cuts down on us repeating ourselves in our code so much. So here's one example of how we're using macros. Rather than repeating this case statement that converts a date to a fiscal year multiple times, why do we do it multiple times? Well, if we're talking transactional data, we might do it once for the donor's first donation date, once for their most recent donation date, once for the date the donation actually came in, and then any other dates that could be associated with, like if it's a recurring start time or not. We just call this macro instead. It results in less and cleaner SQL, but also standardizes how the fiscal year output is going to look across columns and models. And with DBT, rather than that multi-script architecture we discussed earlier, we were using to build all donations at the various intervals, we were able to use the built-in incremental functionality of DBT. So this way, we can specify it via DBT build if we want an incremental refresh or a full refresh, but it's the same SQL file, so no more maintaining 3 just for one model. And this is all now orchestrated via Daxter, and that's replaced our cron jobs for scheduling and running our models. We're also using macros in Jinja to further define what happens or how much data is getting pulled for an incremental run. And we even have custom rules defined in the Jinja for development schemas. All the down and upstream models are also able to take advantage of this incremental functionality. And this has cut down greatly on the amount of files my team and I need to create and maintain for just one model. And thanks to lineage graphs, we can quickly see what models depend on others rather than having to really fully read through or run out of the SQL every time we make a change and just hope for no errors. And the associated YAML files for each model also brings some advantages. Namely, we're able to add descriptions to the model and individual columns, which is great if you're developing a column that someone else had worked on, but it's also great for our end users as we're making these visible in our BI tool. So a user, if they're going through and looking in our BI tool, they can see what the column is supposed to do, so it makes self-service easier. And this was also an ability we did not have in our previous setup. And of course, we're defining tests in the YAML files, makes QA quicker, and elevates failure so we know what's going on. And we're also using seed files, which have also allowed us to replace many case statements and even some of our more basic models altogether.
Thanks. So now I want to share some takeaways from our journey so far. First is set up logging and alerting early. It's really hard to diagnose issues, especially across multiple systems, if you don't have any visibility into what's happening. Second, compared to a tool like Snowflake, which has really pretty UI, nice docs, lots of quality of life features, Trino, for example, has a pretty bare bones, weak UI, relatively few resources for getting started and tutorials, and also performance tuning can be a bit more opaque as you have so many options. But shout out to Trino, the definitive guide, great resource. 3, experimentation can drive performance. We found actually that reducing the number of threads that we ran in DBT from 8 to 4 improved performance because it was creating less load on our Iceberg Metastore database, which couldn't really keep up. So our jobs ended up completing faster and caused fewer errors just by reducing the threads, for example. Fourth, consider the total cost of ownership. There's a trade-off between building with open source tooling and managed SaaS platforms and tooling. On the open source side, you're paying for engineers to do the work of implementing, deploying, and maintaining these batteries not included tools and software. On the managed service side, you pay a premium for the convenience of the managed services. So before you decide to use open source tooling, make sure that you have the engineering resources to do so and do the hard work of connecting the systems, troubleshooting bugs, and deploying the infra. And finally, this is going to be obvious to some, but if you don't know it, the main driver of our query speed improvements came from switching our query engine from the row-based MariaDB to the columnar Trino query engine and keeping the data as Parquet files in object storage. So, as a first step, if you're looking to increase query performance, consider copying data from your application database to a system designed for analytics and run your queries there. That is our talk, folks. Thank you all so much for joining us. If you've used Wikipedia or any related projects, please consider donating to keep knowledge open and accessible by following this top QR code. If you haven't used Wikipedia before, check it out. You might learn something really cool.
Nice.
Finally, this changes by the day. Hopefully it's still accurate, but I believe we're still hiring for data roles across multiple teams at the org, so you can follow the second QR code to check out our careers page. Thank you all so much, and please don't forget to take the survey. And I think we'll now take questions.
Yeah. All right. Elson's going to run the mics over.
Okay. Getting the mic stuff figured out.
The mics, by CEO, you're first.
You could tell us.
So do y'all look into the MariaDB call store as an option for just to switch the storage engine and keep the rest of the stack the same?
I don't believe we did. No, we didn't.
Yeah.
I was curious. I haven't played around with it myself either, but I know that I think it's less mature than the row store storage engine for MariaDB, but you touched on it at the end, but you could use it might be an easier slotting replacement for some folks who have that same stack.
That would totally make sense. I think also Trino is nice because it really integrates with all the other tooling, and there are resources specifically for analytics. That might be the case for MariaDB too, but I'm not sure.
It's great. You got a bunch of other advances as well.
Yeah.
There's a lot of other improvements. So.
Yeah.
Ooh, very cool.
So important to note, the Civi CRM is still running on that MariaDB, right? So I think it would have been a bigger ask for our tech team to do that rather than just migrating to the distributed query engine. But also it gives us the ability to pop into Kafka and things like that too.
Oh yeah, if you're still running transactions.
Exactly. Yeah, so we couldn't change our tech team stack. We could only kind of change ours. So it was just a dump the data over situation. Yep. Of course, thank you. Yeah. Oh,
sorry.
Whoever has the mic gets to.
Yeah, sorry. I see that you use Dagster to orchestrate things. How did you use it to get your data out of MySQL into Trino?
So maybe you can fill in the technical part. What we're doing actually is we're querying the data using so our sources. We're moving over from the MariaDB to MinIO so we can query in Trino. We're doing that with DBT, so it is orchestrated with Dagster, but it's just a DBT job that's a part of our daily run. So it dumps all the data over, then our mark's built after.
And that's part of the good thing about Trino too, is because it's federated, we just run the queries from Trino directly on MariaDB, and then the outputs get stored into MinIO, where Trino can continue to do its thing later on.
Yeah.
Oh, okay. So you have no copy of the source data other than in MariaDB.
Just what's in the MariaDB, and we refresh that. We rebuild what's in the analytics database, essentially, what's in MinIO every day. Cool. Yeah. And it's also important to note these are mostly materialized as tables. I think we have 62 models, only 4 views, 22 are incremental, the other 36 are just tables. So we're dumping the data completely.
I was curious, you mentioned an example where reducing the number of parallel threads actually improved performance by reducing the reload on Iceberg. I'm curious, with, I guess, a format like Iceberg, what are some other kind of low-hanging fruit wins or optimizations that had large impact? Did you discover, and how did you figure those out?
Yeah, I mean, I think moving to columnar storage and a query engine specifically designed for analytics was the big one. Other things that we found, mostly for me on the infra side, really messing around with the JVM configs for Trino to set the heap size and how much active memory could be used by Trino. I saw some decent performance gains. Also, honestly, keeping on top of the updates for Trino solved a lot of our problems. Like a lot of the instability that we saw in Trino would be fixed like a month later in the latest version.
Easy question.
Yeah.
What's next for you guys? What problems are you tackling next?
We're tackling the problems of a growing analytics team. The team has also grown at this stage, right? It was just a couple of us, now there's 4 of us. And just also like, to be honest, like the problem of like having now like the data lake and the product of the data lake and the things we can do faster there, deciding what should happen on egress, what should still happen in the CRM versus what an analytics engineer actually should be transforming, what needs to be in the source of truth, what doesn't. That's kind of what's next for us, as well as just like really having the time to like really deep dive in, like help with our audience development strategy, things like that. Like time being able to do like the prescriptive analytics rather than just like saying this is what happened. That's what's next for us.
And I think on like a little further from the analytics end, the new like Dagster makes it much easier for me to deploy utilities for other teams. So for example, we service questions from all over the world in various languages for people complaining or thanking us or just inquiring about Wikipedia. And so I'm building like a tool that will automatically translate macros in our in the tool we use to service these requests.
Zendesk.
Yeah, Zendesk to automatically translate these to load the translated responses over into the tool instead of manually copy pasting. Having a tool like Dagster that's really flexible in scheduling and things like that is really helpful for me too.
We also have the Google Sheets integration, which is
the
good
Google
for
Sheets
teams.
integration.
Yeah. Any other questions?
One up here, one back there.
Yeah. Yeah, I think we have time for these two. Yeah.
Yeah, one of the nice benefits that I heard about with Iceberg is the ability to time travel. I was wondering if you guys found any like good use out of that feature.
I don't think we have yet, although I think it'll be nice if we ever have to audit our data, certainly. I don't think y'all have run into any serious problems with models that would require like really going back in time to check the data, but I imagine if that happens, it would be really helpful.
It will be, yeah. I don't think we have that's one use case for it. I don't think we've come up with a ton. This change is new, right? But also we're dumping the data fresh every day, dropping it. The source of truth is still the MariaDB. But that would be helpful for the tech team to start having that. Yeah.
Yep.
Thank you.
Yeah.
Back here?
Yeah. I think this question will take us to time, but we'll see.
We can go over it.
Yeah.
Yeah, I saw in the diagram you use MinIO and Iceberg. So would you share why you use MinIO? Was a problem you used to fix?
Well, just part of the lakehouse architecture requires storing your data somewhere else. And we were looking for a self-hostable open source solution. So MinIO fit the bill. You know, it's not fully compatible with like every tool in the modern data stack, but the API is S3 compatible. So I think that makes it easier for a lot of the tools to connect to it. But I think you would be just fine using something like Ceph also or other object storage solutions. But MinIO seems to have some prominence for better or worse.
To the Iceberg, the metadata is stored in MinIO, but how about the packet data? Where is it stored? If it's very large, is MinIO can handle the very large data?
Yeah. So and just to clarify, actually the metadata for Iceberg, part of it, like the manifest JSON files and things, are stored in MinIO, but there's still the metastore database that is in MariaDB. But as far as the actual data files in Parquet, yeah, it's just like S3. You can just dump large amounts of data in there, and as long as the servers that we have like bought for the purpose can, you know, as long as we have the space, then it can hold all the data, and it's like very performant.
Yeah, we have an issue with the metadata. So when the table gets large, actually there are many manifest files. So do you have a similar issue? How would you make the metadata or the Iceberg table smaller and maintain well?
Yeah, we haven't run into that issue yet, although some things top of mind for me will be scheduling some background compaction jobs and expiring snapshots also, and not keeping a full history probably, so the manifest won't get like massive.
Yeah.
Yeah,
Okay.
Thank we're not there yet, but like I'm waiting for those errors to come, or like for the 5-minute scans for the metadata to come.
Yeah. Okay. Thank you.
Anyone else? Over here?
Hi guys, I have a question. Did you deploy this on standalone nodes, or did you do this on a cluster since it's on-prem?
Yeah, so most of the tooling are deployed on clusters. So Dagster is an exception. We just have that on one main server, and then we have another one for like failovers if that fails. Otherwise, though, right now we're at a data size where we have 1 coordinator node and 3 worker nodes for Trino. So that's one cluster. And then it is the same thing for the MinIO servers also. We have 3 MinIO servers times 2 for the failover.
All right, and that's all in a self-hosted K8s cluster.
Exactly.
Yeah.
Yeah.
All right.
Yeah, we get a pretty sick deal. It's like $3K per machine over 5 years. So pretty good cost, I think, compared to like a tool like Snowflake.
And I have another question regarding authentication and access control. How do you guys solve that problem? Do you authenticate in the catalog or in Trino itself?
Yeah, we have users in Trino, and just to access Trino, you have to SSH into the remote server, so you'll have to use a YubiKey, you'll have to know your passphrase. Yeah, we're thinking about integrating some of the tools into Okta, like maybe Metabase, or the tools that, you know, for folks who don't need individual Trino users, we're probably going to put some kind of like SAML or SSL authentication on top of it. But it's all self-hosted, so you need like an SSL cert already installed on your machine to even like not get like a 404 error or a 401.
Well, do you plan to let the users actually query your Iceberg tables directly?
So what
Or
we're-
it's mostly via the dashboard?
It's going to mostly be via dashboard. Through the dashboard, through Metabase, you can write SQL queries. I anticipate most of our end users are not on the more technical side. That would be us and the analysts that were doing that. We want to make sure that Metabase is set up in such a way that they can self-service through there. And there's a user for Metabase that has certain accesses only to what we call our core tables, the ones we actually want users to interact with, rather than some of the junk that could be in the sources.
Although I'll say, I think we're talking maybe in a future project about sharing some of this data outside of the fundraising team with the product and tech team.
Yeah.
And those are like lots of folks who know Trino or Python or SQL. And so we'll probably give them limited access, but their own users for it.
Yeah.
Yeah, all right. Thanks, guys.
Yeah.
Anything else? Any other questions?
Going once.
Cool.
Going twice. All right.
Thank you
Thanks
all
for
so
coming,
much.
everybody. Really appreciate it.
Have a good one.